our Managing Trustee, Sirajuddin Ajmal Sahab, the Honorable MLA of Binakandi and former MP of Borpeta, to felicitate our youngest professor in a very loving Assamese traditional way with a gamusa, a chapi, a korai, a pet, and of course a token of love from Ajmal Foundation with an Ajmal perfume. Dear students, he is the youngest professor, a scientist. So, a standing ovation for our guest, Professor SOBORNO ISAAC BARI. And an applause, the vibration of which we shall carry back to New York. Welcome, 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 Mr. Bari.
Small present from Ajmal Perfumes for you.
I will now take the opportunity to invite Mr. Rashidul Bari to the dais and request Mr. Jahidul Haq Chaudhary, the manager of Ajmal Foundation, to kindly come up and felicitate Mr. Rashidul Bari, the father of our youngest professor, who himself is a legendary and iconic figure. Sir, we welcome you and we felicitate you in a very traditional, loving Assamese manner. This was indeed an extraordinary gesture. Sir, we also have a token of love from Ajmal Perfumes and would like to tell you that Ajmal Perfumes is the leading perfumery in the world, and this is just a token of love to tell you that we are truly grateful to have you here. May this perfume carry the fragrance of your visit to Assam that you will cherish forever.
Like father, like son.
Yes, indeed, like father, like son. He's truly happy to felicitate his father with gamusa. Thank you, thank you.
Proud of you.
Thank you so much. Now I request Mr. Pranish Devnath to kindly come up to the dais, and I request Mr. Abdul Qadir, the project head of Ajmal Super 40, to felicitate Mr. Pranish Devnath. Sir, we welcome you to Assam once again, to Ajmal Foundation, to Nazir Ajmal Memorial College of Education. Dear students, please extend a round of applause to welcome Mr. Pranish Devnath. Thank you, sir. Thank you so much.
You deserve it, sir. Please. Thank you.
It is now time, as Sir Arif sir has mentioned, that this is indeed a day that will remain in your memories forever. We will have a session by our youngest professor, Professor SOBORNO ISAAC BARI, and to invite him, I would dedicate a few lines. With honor, we welcome you today, a guiding star lighting the way. Your wisdom and grace, a beacon bright, inspiring all with your shining light. A leader with vision strong and true, we celebrate and learn from you. Your presence here is a gift to all. In gratitude, we all stand tall. Thank you for your time and care, for being with us and the values you share. Today, we honor you with hearts sincere. Professor SOBORNO ISAAC BARI, you are so esteemed and dear to all of us. Ladies and gentlemen, with a round of applause, please welcome the youngest professor of the world, Professor SOBORNO
Mic, please. Sir, Professor Sir. Professor Sir.
Am I audible? Am I audible?
Yes, yes.
What does this mean? I'm not an IT person. Can anyone help with this? Oh, here it is. Okay. Greetings to Sobono ISAAC Namaste to everybody here. It is my honor to be here at Oswald Memorial College of Education. So, today I'll keep the introductory talk short. And I'll also keep the scientific talk very short. It will only be maybe 20 to 30 minutes. But today, I'm going to talk a little bit about satellite light tensors. Oh, this is some very nice writing. So, today we're going to be talking about tensors, tensor calculus, and how this relates to the foundation of relativity. I can write in cursive. Great. So, oh, it's even touchscreen. Wonderful. So, I suppose I'm going to have to use one word. So, let's see, can I change the thickness? Zoom? Can I zoom out anymore? No. Okay. So, what is a tensor? Well, imagine this. Does everybody know what a scalar is? Yeah. Say it louder.
Anybody? Oh no. This is huge power. Well, I guess I'll have to yell.
No, you don't have to. We'll provide a microphone.
Go to the audience. Okay.
Do you need a mic? The one that you can reach?
No, he cannot do both.
Okay.
Oh yes, you underestimate me.
So, I'm going to take this off real quick.
Whose microphone is this? Oh.
Okay, so, does anybody know what a scalar is? Raise your hand if you know what a scalar is. Nobody? You guys are not going to pass the JD. So, what is a scalar? Well, essentially, it's just a value. Okay. Can anyone raise their hands? Does anyone know what a scalar is? Okay, maybe it's just
Over there.
Oh, okay, a few people, maybe. But it's not a majority of the audience, so I'm going to have to explain it. So, a scalar is essentially just one value. It does something like 3 or 7 or 191. Can anyone give me a few more examples of scalars they can think of? Anyone raise their hands if they want to answer that? Anyone? Raise your hand if you want to answer that question. I know, man. I'm trying to facilitate audience participation, so if you could please raise them high. No one can think of examples of a scalar from what I've given. Can everybody see the board? Oh, okay. There's one guy in the back over there, so. Okay, whole numbers is a good start, but the thing is, a scalar is just any number. So a scalar is just a singular value. It can be anything on the real number line. It can be in this direction or in this direction. So it could be -5, or it could be e, or it could be square root 2 to the square root 2 power. Doesn't matter what it is. That's what a scalar is. So, a scalar is just any real number. But now, let's move to the concept of vector. Does anybody know what a vector is? Raise your hand. Okay, I see somebody. So can you keep your hand raised so I know where you are? Okay. Let me see. Should be somewhere over there. Student direction. Okay. Great. That's the textbook definition. All right. So that's not exactly what I was looking for, but we can work with it. So it of course has magnitude and direction. And how do we describe the magnitude and direction? Well, the magnitude is just the length of the vector, and the direction is what angle it's pointed at with respect to the x-axis. So, we can actually specify these using the components of a vector. So the components of a vector are essentially the lengths of the projections of the vector onto the x and y axes. So this blue line right over here is the x component, and this green line right over here is the y component. So we write it like this: x comma y. And of course, the length using the Pythagorean theorem is simply square root of x squared plus y squared, and this is simply arctan of y over x. So we know what a vector is. At least we know what a vector in 2 dimensions is. But in general, a vector is just any array of numbers. It can be a catalog. Of course, it can't be an infinite catalog. That's just to say, not a vector. But it's just a catalog of numbers. 4, 7, 3. And the same number can, of course, repeat twice. Now, of course, this is an 8-dimensional vector, so obviously I can't draw it. But we all know what a 1-dimensional vector looks like. This is just a scalar. A 2-dimensional vector is something I've just demonstrated. And the 3-dimensional vector is quite easy to visualize as well. You just draw the 3 coordinate axes, x, y, and z. You get the x coordinate, you get the y coordinate, and you get the z coordinate. And that's the vector. So, this can keep going past the 3rd dimension into any dimension we want. So, the best way to specify a vector is just going to be v. And to show that it's a vector, we're going to draw a little arrow sign on top of it, because vectors usually look like arrows. So, this vector is just an array of numbers. Now, how do we know which, let's say we want one specific component of the vector. Like, for example, in the vector 2, 5, say this is vector v, we want to specifically obtain this number, 2. Does anyone know how we get that number? Anybody? Raise your hand. How do we denote the x component of the vector? This lecture is going to be a lot longer than I expected. Nobody knows? Come on, don't be scared to answer questions. It's not like you're going to be wrong all the time, right? And of course, being wrong is anyway how you learn. Anybody? Oh, okay. Yeah, you have.
The rectangular coordinate system, we denote the x coordinate by using unit vector. I guess.
Yes, okay. That's a good start, I guess. But what I was more saying was, how do we get the 2 in specific? And of course, as he said, this can be denoted like this. But that's not going to apply to n dimensions. So instead, what we write this as is Vx. But here's the problem. Eventually, at some point, we're going to run out of letters. There are only 26 of them. So just use Greek letters. But there are only 24 of those. So just use Hebrew letters or something. But there are only 30 of those. At some point, we need to generalize it. So what's the only thing that doesn't run out? Numbers. So if the x component is the first component, we're going to denote it instead as v sub 1. Thank you.
I have a doubt.
Yes.
You are using a lot. You are using numbers a lot, but I don't know the actual meaning of actual definition of numbers.
Okay, got it. So we have this vector 2, 5, which we are going to define in the coordinate plane. Of course, 2 is just going to be the x component, right over here. And 5 is going to be the y component. Oh, by the way, a side question. What standard are these students in?
9.
Oh, okay. All right, sure. So, we have this vector right here, which goes 2 in the x direction and 5 in the y direction, right? So, then, if we want to access the x vector, the x direction, we then have this component right over here, vx. And here's what we're going to do, actually. Instead of using letters, which we all know run out super quickly, instead we're going to use numbers. So x is the first component, x is the first coordinate, so we're going to call it 1, and y is the second coordinate, so we're going to call it 2. So vx becomes v1, and vy becomes v2. This is just so we can generalize it past the second and third dimension into however many dimensions we want. Alright, so that's how we denote the components of a vector. But now I'm going to do a little bit of a switch in notation. Actually, I think it's better we just stop with covariant and contravariant measures instead of getting into calculus. So we have v right over here, our vector. And instead of using subscripts, we're going to use superscripts. And the reason for this is going to be apparent later, but just go along with it for now. This is going to be a superscript. So this is just going to be v1i plus v2j, if we're in 2 dimensions, of course. Or if we're in n dimensions, here's what we're going to do once again, to generalize. Because I and j are the basis vectors in the second dimension, in the third dimension it's k, but then in, say, the 27th dimension, maybe you can use all the letters of the English alphabet, but you still have one basic vector left. What do you use then? So, instead to generalize, we're once again going to be using numbers. I is going to be E1, J is going to be E2, and K is going to be E3, and so on and so forth. So we get V1, E1, plus V2, E2, and so on. So this is going to be, if we have just n components, we get Vn, En. Right? So this is going to be how we write any vector. So now what we're going to do is explain the concept of covariance and contravariance. Imagine temperature in a room. So imagine we have a room, and let's say it's hot in this side, and eventually it gets colder in this side. So what we're going to do is we're going to describe that temperature using a scalar field. A scalar field, and essentially what happens is that every point in space is just assigned a scalar, a number. So, if it's hot in this side of the room, the temperature as a scalar would be, say, 200. And then it goes down over here to maybe 190, 190. And as it cools off, eventually over here it's going to be 0. And maybe even negative as we go even further. And of course, remember, they're not just at the lattice points, they're everything in between as well. So, a scalar field is just a field that assigns a number to every point in space. So an example would be f of x comma y on the 2D plane is equal to 3x plus 2y. And of course, this is a scalar field. Why? Because you can just take any old number, any old point. Let's say we get 7 comma 2, for example. So, if we plug in 7 comma 2 here, we get a scalar. And that scalar that we get out is going to be 25. 7 times 3 plus 2 times 2. So, this just assigns a number to every point in space. And you may have seen any scalar field visualized as a surface or a three-dimensional function. I think I'm going too far, actually. So, the surface is just graphing the three-dimensional coordinate plane, like this. So, as you can see, this is just the surface in our coordinate plane. Go to a ring in between lines. Okay, great. So, this is our surface. And now, what does it do? Well, the height above the ground on the z-axis is just the scalar assigned to that point on the xy plane. Alright, so now, imagine we take some random point on the surface, right? And let's say the value right over here is, I don't know, x of x1, x naught comma y naught. Now, what I'm going to do is, I'm going to do a little sneaky thing. I'm going to go in some random direction, going to put a little differential there, going to take a tiny step called ds, and go to a new point. Here, the value is f of x1 y1. So now, all we're going to do is we're going to take the derivative. We're going to take f of x1 comma y1 minus f of x naught comma y naught divided by the magnitude of the x. Which is, of course, you can calculate that from the Pythagorean theorem. And so, that's what we call a covariant vector, or a covector for short. It's just a vector with the magnitude of this derivative in the direction of dx. So essentially, a contravariant vector is just a regular vector, the one with magnitude and direction we just talked about. And a covariant vector is essentially like taking the derivative of a scalar field. All that means is we have this field of numbers 1, 3, 5, 0, 7, 2, 6, 1, 0, 3, 1, 2, 3, 4, 5, and so on. And we go from some random point A to some random point that's just nearby, called B, and we measure the change in the scalar field between those 2 points. And as the magnitude of this vector approaches 0, we get to find the magnitude of the covariant vector. So this is essentially like the derivative over a contravariant vector. If you've ever taken calculus 3 or multivariable calculus, you'll find that it looks like partial of this function in some random direction, dx. So we're going to call that some vector, v. And so that is what we call the directional derivative, also known as a covariant vector. So I have a feeling that if I go beyond this point, most of you won't understand. So this is where we're going to end with the notion of a contravariant vector and a covariant vector. So once again, just to review, a contravariant vector is just a vector, it's just a regular vector, magnitude and direction. And the covariant vector is just a change in a surface, or a change in a scalar field. So, I feel like I may have not considered the level of the audience in today's talk. So, are there any doubts I can clear up in the audience? Does anyone have any questions about what just occurred? Anybody? Yeah, I haven't got the audience talk. Alright, let's see, is there any better way I can teach this? So, a covariance vector is a change in a scalar field. And what is a scalar field? Well, a scalar field is like temperature. Every point in a room has temperature, right? Now, does every point in a room have a temperature? Yes? Can you find some point in a room that doesn't have temperature? Louder? Louder? No. Good. Okay. So, that means that temperature is a scalar field. Now, how do you describe temperature? What is temperature? No, and not the physical definition. Temperature, a scalar, a vector, or something else? Anyone? Louder. Good. Temperature is a scalar. It's just a number, like 37 degrees Celsius. That feels like the temperature in this room right now. So, every point in a room has temperature, and temperature is just a number. So a scalar field is just something which at every point assigns a number. Do you understand? Okay. So now, let's say in this relatively hot room, I take a tiny step from here right over to here. This is what we call a differential step. Here over to here. It's a very small step, and it gets even smaller as you go on. Does anybody here know what a derivative is? Louder? No? Yes? Does anybody know what a derivative is? Anyone? No. I'm gonna get that's a no.
So can you repeat the term?
Does anybody here know what a derivative is? Yes or no?
I'm sorry, I don't know.
Okay. So, here's what a derivative is. Let's say we have a function, yes? So, now, in that function, what we're going to do is we're going to take one point right over here, and then another point right over here. Now, let's say this is x, and this is x plus 8. And this is f of x. Then the y-coordinate here is going to be f of x, and the y-coordinate is 8. So then, what we're going to do is we're going to draw a secant line between these 2 points. Right? It's a line that goes through both of these points. And we're going to take the slope. Everybody here knows what the slope formula is, right? Okay, so, can you guys tell me what's the slope of this red box? Okay, let's start from this. What is the slope? What is the slope formula?
It is the rate of change of y with respect to x.
Okay, so that means it's just going to be the change in y divided by the change in x, right? Good. So then, the initial y value is f of x. The final y value is, anyone have an idea? Louder. Good. And we divide that by the difference between the final, which is x plus 8, and what's the initial? Louder. Good. So then these two just cancel out, and we're left with what we call a derivative. But this isn't a derivative quite yet.
Because 8 is a number. But what we're going to do is, this number is going to get closer and closer to a certain point, and 8 becomes closer and closer to 0. So in the same way, we're going to, instead of taking a little step, specifically in the x direction, as you can see we did here, we're going to take a little step in any direction we want. Like, let's say I'll use that direction, right over there. Look to take a step in that direction, and then go back here. I can feel the temperature here, and then I can feel the temperature here. It's a very small change. So, what we're going to do is we're going to take f of, let's say we have the initial coordinates, plus our little differential vector dv minus the initial coordinates divided by that little change, dv. And the thing is, the direction of that vector is going to stay the same, but the magnitude is going to go from a large step like this to a very small step to an even smaller step, and eventually it's going to approach 0, just like 8. Hopefully I haven't lost anybody. So, that means that we're just going to take a very small step in any direction. We're going to record the change in temperature. Then we're going to divide that by the magnitude. And we're going to keep the magnitude getting smaller and smaller and smaller. And so, what we get out of this, the limit, is going to be the magnitude of our covariant vector. So, essentially, what we're doing is we're pointing in a direction, we're taking a very small step in it, and then we're recording the difference in temperature between here and our original position, which is of course very small. Then we divide the small change in temperature by the small change in direction, by the small vector, specifically the magnitude of the small vector. And then, once we get the value of that, we make our vector in the same direction, but instead of a big step, it's a small step. It becomes even smaller and smaller, until the 2 points are virtually indistinguishable. Then the direction of our covector is parallel to our little ds, and our magnitude is equal to the limit of this. So, hopefully that's a bit more intuitive of a definition. All that it is recording how big a change is in temperature. So, if the temperature changes a lot between this side and that side, like let's say we have a snow, like let's say we have a desert bordering snow, then if the temperature is really cold on this side and really hot on that side, then the derivative as we walk from here to there, the covector is going to be very large. But if the temperature is generally the same all around, it's 30 degrees Celsius right over here, and it's 30 degrees Celsius over here as well, then there's not going to be any covector. The covector magnitude is going to be 0 because there is no change. There is no derivative. Does everybody understand that? Okay. So that's where we're going to end off today. So that's covariant and covariant vector. Thank you everybody so much, and I hope you definitely learned something from this lecture. Understand?
He will take 10 questions, 10 math questions. So please make a line for those of you who want to ask him question. So, Dada, can you give them instruction?
We will have a question answer session. So dear students, please ask question. Over to Pranesh sir.
So,
they're going to make a line.
yeah, I'm fine. Good afternoon, everyone. How's the Josh? How is the Josh? How is the Josh? Yes. So it's a privilege for us that Professor Isaac Bari from New York University, USA, he is here in Assam, now in Hojai, and one of the prestigious institutions, run by the Azul Foundation. So you have been lucky to have Professor Isaac Bari in your institution. Am I right or wrong?
Yeah.
Right. So, Professor Bari want to have an interactive session with few of the students with the questions like in physics and mathematics. So, we're having the 10 questions can be selected. So, 10 students can we have volunteer yourself with the questions in physics and mathematics. So, please come here. 10 students. Make a line. 5 from this side, 5 from this side. Yeah, 5 from this side. You make a line here. You make a line here. We'll do it academic. You make a line here, 5 and 5. 10. And questions restricted to physics and mathematics only. Physics and mathematics. Whatever type of tough questions you have, and some questions you want to solve solutions from Professor Isaac Bari, you can have this thing. So 5 this side and 5 this side. 10 questions can we take? We can take. So come forward, make a line, Thank you for showing your courage. Yeah, please look up.
Okay,
Come also, please make up. Yeah, please join us.
Task has the priority.
Last one the priority. Yeah, please. Yeah, 10.
5 plus 5 5. I'm sorry. 5 plus 5 5.
Yes.
Oh, you don't want to go other side.
Yeah.
Go other side. 5 plus.
So this is the golden opportunity, and congratulations to all 10 of you that will be interacting with the renowned professor, youngest professor of the planet, as told by Professor Principal Arif Mahmood Ali Khan sir. So congratulations. So one by one questions can be asked to Professor Isaac Bari, and make sure that your name and class and yeah. So can you start the session now?
Ladies first.
Ladies first. Okay. Counselor. Yeah. So who is the president now of India? Who is the president? Is it lady? Yeah. So proud of you, no? Yes. So now question session start from you. Your name, your class, and question. Thank you.
My name is Nisha Taslim. I'm from 11th standard, and sir, my question is quite insignificant compared to whatever you know. We don't have very much knowledge about dimensions. We're just learning very basic things about 1D, 2D, and 3D. But there are around 26 dimensions, or maybe I am not much. I just wanted a little brief about what are dimensions. Like from 4D onwards, like we know about the X, Y, and Z axis of 3D. So when it will be 4D, what is the extra axis that will come, and just a little briefing about dimensions and all.
Of course. So let's say I pick up this tissue box right over here. So then this tissue box looks like this, right? This tissue box looks like this. And of course, I'm the best artist in the generation, so you can obviously tell this what it is. So this is the length, this is the width, and this is the height. All we mean by 3 dimensions is 3 metrics that we use to specify the size of any object. So, using the length, width, and height, we can say that this object has some sort of size. And the reason we use that perpendicularly is very simple. It makes our volume and area calculations very easy. So if we have a sheet of paper, usually the thickness is negligible. So we talk about the 2 metrics that we measure with. We measure via the width and via the height. And so, if we're at 4 dimensions, then we use 4 metrics to measure this. But of course, we haven't come across any objects that need that in the real world. And so, since we don't need it in the real world, we can't imagine what it would look like on a sheet of paper or a smartphone. It's a very nice question. And actually, the reason I said, what if we're in the 27th dimension, which apparently seems a little bit confusing. This essentially just means we have an object that needs 27 perpendicular axes to measure. Of course, there's nothing like that in real life, and there probably never will be. But this allows us to generalize any vector. Because the vectors that we have in our life usually have 2 components, or maybe 3 components. But it turns out in general relativity, most vectors have 4 components because they have to account for time. And if we were doing general relativity in any other dimension, it would seem to be useful for other applications like string theory. We could have even more than 4 dimensions, maybe even 12. So, we just generalize any vector because it makes things easier for us to do in higher dimensions, which we often need to do when considering theories that utilize higher dimensions. Of course, we already can see 3D in real life, but when it comes to 4D, which is what general relativity often uses, we can't actually visualize that. So we simply have to generalize it. When it comes to, for example, string theory, which has 11 dimensions, or so I've heard, that we need to generalize that even more, because that's beyond human imagination. And finally, when it comes to the axis that is beyond x, y, and z in 4 dimensions, doesn't have an official name, and any official name isn't important, but most people often call it W. So thank you for the question. It's very interesting. Thank you, sir.
Thank you for your, nice question, Rich. Next question, your name?
Oh, no, other side. Sir, other side.
That's right.
So, one point.
Okay,
Yeah.
one from this side, from okay.
As a go.
So, next question, I need.
Good afternoon, sir. I am Mohammed Muaz Laskar of 12th standard. My question is basically related to physics. Well, it's not a physics question. No. We all dream. We see some visuals. My question is, how do blind people dream? Do they dream, or how do they dream? If they dream, they need to see something. And if they can't see something, how they see something?
Well, that's more of a psychological question, but I guess that blind people dream, because obviously dreaming isn't using your retina. Most blind people don't just completely see black. Instead, they have like clouds in front of their eyes, for example, that don't allow them to see anything except their peripheral vision. So thus they're legally blind. In that specific case, we call it cataracts. But in our dreams, we obviously aren't using our real eyes. So instead, we're just using our imagination. Of course, I don't exactly know how dreams operate, and I believe that leading psychologists don't know either. But I don't think blind people or people with cataracts dream with little clouds in front of their eyes. Although you obviously have to ask.
That means that they only see the clouds in their dreams, but they don't dream.
Well, you have to ask a blind person.
Right answer. Correct. I will not know.
Thank you.
Next, lady.
Next,
Math and physics. Math
Math
and
and
psychology.
physics,
No
not
psychology.
technology. Especially, I encourage to ask questions from mathematics.
Hello sir, my name is Shavana Nasmin Chaudhary and I am in 11th standard currently. My question is that the theory of relativity is of course very complex and a lot more than we expect it to be. And how would you just give a brief idea about relativity to a person who doesn't have much knowledge about it?
Okay, sure. So essentially, what relativity does is it's all based around what we call the field equation. And this field equation is just an equation with a bunch of variables. And most of these variables are just matrices of some random numbers. And these numbers encode everything from the electric field to the magnetic field to mass to energy, so on and so forth. So they're like little encoding of everything that's going on in the universe around us. And essentially, all of these numbers and matrices surround one specific variable, which we call the metric tensor. This metric tensor is actually a matrix. This matrix is just describing how space-time curves. And in response to space-time curving, objects are going to roll around. and response to objects rolling around, space-time goes to curve due to their own mass. So this is all equal to a proportionality constant times all of the mass of the universe. So essentially, all relativity is saying is we have an encoding of all the information in our universe, and the variable we have to solve for is the curvature of space-time. Now, in practice, this is impossible to solve without computers. Even with computers, we can't really get close to encoding our entire universe, but it has proven to be correct through a few tests of smaller equations. So, it's I don't know if that's a good overview of relativity, but that's basically what I do.
Yeah, next question. Now I complete one group. So next question. Yeah. So,
Ooh, that's a hard one. Okay. Minus 1/2 plus 1/3 minus, oh wait, no, never mind, that's pretty easy, I think. Okay, so what I saw there was minus 1/2.
It is everything.
Oh, okay. Minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6 plus 1/7 ... So here's my thoughts about solving this equation. So, of course, you can already tell, and here's what I'm going to do. First, I'm going to add a 1 to this side. Let's say this is x. We're going to add a 1 to this side. And so, 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus 1/6. So this is a little bit hard to think about, but what I'm going to do is going to put 1/2 plus 1/12 with okay. So this is 2/2 minus 1/2. Let's see. Okay, this is actually kind of difficult. What do we think this? Alright, so what I'm going to say is minus 2, minus 4, minus 6, minus 8, etc. It's just going to be half of the harmonic series, which itself diverges. And 1 plus 1/3 plus 1/5 plus 1/7 also probably diverges. So, okay, let's see. What can I do to solve the alternating harmonic series? Well, let's see. This is a very tricky question, actually. So, I think we can solve it using telescoping, though. So, we have 1 minus 1/2 is equal to 2 minus 1/2. We have 1 times 2. We have 1/3 minus 1/4 is equal to 4 minus 3 over 3 times 4, and so on and so forth. So what's actually going to happen is this is going to be 1 over 1 times 2, plus 1 over 3 times 4, plus 1 over 5 times 6, plus 1 over 7 times 8, and so on and so forth. And hopefully I can figure out how that telescopes pretty quickly. So I'm pretty sure this converges. Just to be sure, I'm going to write it down. So AN is just going to be equal to, this is A1, this is A2. So this is just going to be equal to 1 divided by 2n plus 2n minus 1. That means AN plus 1 divided by AN is equal to 2n times 2n plus 1 divided by 2n times 2n minus 1. Is it going to be 2n plus 1 or 2n? No way, this divergent. Oh, I think I did this the wrong way. AN plus, wait. If AN plus 1 divided by AN is greater than 1, that implies that AN plus 1 is greater than, no, that's wrong. That's definitely wrong. So let's see. We have 1 over 2 plus 1 over 12 plus 1 over 30, so on and so forth. And so, oh crap, I'm dumb. Very good. Okay, so this is going to be 2n times 2n minus 1 times 2n plus 2, 2n plus 1. Wait, that makes it greater. Okay, let's, let's see. So, does this diverge? No, it can't. But, oh wait, no, I have the whole thing reversed. So, this next one is 12/30 of the original. Oh yeah, this would be inversed. Okay. So this doesn't matter. We have 1. Okay, so 1 over 56 plus 1 over. Okay, this is definitely a pretty question. So I'm gonna say this definitely converges, but I have no idea to what it converges to. So let's see. If I can figure it out within this time span, it would be great. But my guess is that I probably can't. So I'm gonna make one last desperate attempt. This is just a half of 1 plus 1/6 plus 1/15 plus 1/28. Okay. Does anybody have any ideas on how to solve this converging series?
Not actually solving this. I am getting two answers from this by solving this.
Let me see that. 2 answers. Okay, what did you get?
Yeah. I use this method. Yeah, I am getting this.
2s1 is equal to, oh sorry, 2s1 is equal to this, 2s1 is equal to 1 plus s1 plus s2, okay, s1 minus s2 is 1, s2 minus s1. Okay, so here's what I think the problem is with this approach, because I'm pretty sure you can't just add them like that, because S1 and S2 are both series that diverge. It is only when they're subtracted do they converge. So you can't really do proper arithmetic in this way. And of course, if you do, you get this paradox that you do get 2 different answers. So don't try to add or subtract diverging series. Instead, that approach might be helpful for what I'm facing right over here, because, of course, I'm still stagnant on. I could be using every even term or every odd term. So my advice is just don't sum or subtract divergent series. That leads you to a paradox of my code. Thank you. Just don't add or subtract diverging series. Both of these diverge. So adding and subtracting them leads to some very bad arithmetic. It's the same way that the sum of the natural numbers on this one goes. So just don't add or subtract diverging series because it leads to not good results, like a paradox. None of your algebra is wrong here. It's just that you can't sum 2 diverging series. It's just that algebra messes up when you consider these. So essentially, what we're trying to do is find the limit of these two. S1 is a limit of this sequence, and S2 is a limit of this sequence. But the problem with S1 is that it approaches infinity. The problem with S2 is that it also approaches infinity. So by multiplying it by 2, you're multiplying 2 by an indeterminate number. So essentially, you're doing algebra with numbers that don't actually exist. A complete paradox of the leaves. So I find to divide by 0. Yes, that's a limit. But the thing is, this series, did I turn it up? This series, oh my gosh. This series converges. This series actually converges to a number. So we're not doing arithmetic with that number. But here, we are doing arithmetic with the numbers that don't actually exist. As you know, the harmonic series diverges, so of course half of it diverges too. So doing arithmetic with numbers that don't exist doesn't really work in comparison to doing algebra with numbers that do exist, like these 2 and 2, etc. So essentially, just don't do that with sums that diverge. Does that answer the question, or do you have any doubts? Okay. So just, I guess, one thing to say is, this approaches infinity, and I don't know what this approaches, but it's probably also infinity. So you can't really do math with an indeterminate number. Oh yes, but that's the same thinking behind the harmonic theory, not approaching infinity. The truth is, the harmonic... So, let me just... A and 1
After life বন্ধ হয়ে গেছে
Yeah, we do have another question. Town hall session in the evening. Yeah. So, shall I continue, sir? Shall we take her question also? Yeah.
From this. So it's a very good question, but essentially this is indeterminate, so you can't use it for that. Yeah, even though it's getting closer to zero, it's not getting closer to zero fast enough. Eventually, all the terms will be approximately the same value, and when you add them up, then you get something that's divergent. So just use this conversion. The limit is an plus 1 divided by an has to be less than 0.
Can you take the next question?
And here's the issue with that. Limit is n over n plus 1 approaches 0 is 1, right? Because you get 3 over 4, 4 over 5, 5 over 6. Eventually, n over n plus 1 approaches 1, right? Which means that at some point, the difference in all the terms is minuscule, which means adding them up will make it diverge. So that's unfortunately the best explanation I can give, but I hope you understand. Thank you.
Yeah. So we have our next question from the girls group. So please ask.
Hi sir, I'm Sedan Azamin, and I've been hearing about you from my aunt from a long time, since that I've been your fan. So I have two questions going on for you. They both are from the physics. And the first question is, it says that mass can neither be created nor be destroyed. But in if an object travels in the speed of light in vacuum, then the mass of the object increases. So can you give me a summarized explanation? You don't have to be brief about it.
Okay, so just a summary of. So what's the question exactly? What is the sense of the question?
So if object travels in the speed of light in a vacuum, so will the mass of the object like increase?
Okay, so essentially it would take infinite energy for an object to travel at the speed of light. But yes, as an object's speed approaches the speed of light, then its mass approaches infinity as the gamma factor approaches infinity. So essentially, its mass from an observer's reference frame is going to be infinite, which means it's basically impossible for something to travel at the speed of light as well as have a mass. Photons don't have a mass, but they still have momentum because of the energy that they inherently hold. So it's impossible for anything to travel at the speed of light, but as you approach the speed of light, the limit of your mass becomes infinity. So yes, it does increase.
So the mass increases, right?
Yes.
So there's one more question. Sir.
What is the state of matter other than solid, liquid, and gas? Okay. So essentially, we only consider solid, liquid, and gas separate because they have much different behaviors. Solid has very rigid and brittle bonds. Meanwhile, liquid doesn't have any bonds between molecules. Solid has bonds between molecules. Liquids have no bonds between molecules. But they're still held together by intermolecular forces. But in gases, the molecules are all traveling so fast that there are no intermolecular forces to hold them together, and so they disperse. And so after gas, it can't get any hotter because the intermolecular forces just get weaker and weaker. But some others say that the fourth state of matter is plasma. And plasma is essentially when matter gets so hot, the molecules speed up so much that atoms inside have too much energy and their electrons are ionized. Which essentially means plasma is just ionized matter. So that's essentially the only other state of matter that there is. But still, plasma usually acts the same as liquid or gas. You know, as gas, sorry, not liquid, sorry. Thank you.
Can we move to next question? Can we move to next question? Or
Dear
session will be continued after the
Dear students, we have another session where the students shall directly interact with Professor Bari. Until then, I request the students to please be seated in your allotted seats, and we shall continue with the next session. Professor Bari, on behalf of each and every individual present over here, I would like to thank you wholeheartedly for this brainstorming session. Your insights, expertise has been incredibly productive and inspiring. Your outstanding personality is sure to lift the spirit of every child present over here.